Okay, we're going to talk now about the properties of logarithms, which is actually still the study of the language of logarithms. If you read with me right here, logarithms were very important in our history. Again, I mean for this to be a highlighter. In our history, in order to do technical calculations. I'm going to be able to tell you, again, this is history. There's no question, but historical, even in my perspective, which was my father-in-law, talked to me about how he did mathematical calculations, arithmetic. I'm talking about finding square roots. I'm taking and raising numbers to powers because he didn't have a calculator like we had. So we're going to study a little bit of history and how important they were to our world, or we wouldn't be where we are today if it weren't for logarithms. So we're going to do a little bit about that as we end this chapter. Remember for right now that a logarithm is an exponent, and naturally it will behave that way. And we'll look at the laws of exponents. So we're going to be looking at a product, the logarithm of a product. And so what I'm saying here is to remind you that because they behave like exponents, x to the second times x to the third would be x to the fifth, but 2 plus 3 is what I'm going to write, that I would add these. So I'm going to prove to you that it would be true that the log of 25 times 125 could be written as the sum of two individual logarithms, the log of 25 plus the log of 125, just like here where I was multiplying and I could add. When I'm multiplying, I can add the individual logarithms. I would have to insert the base of 5. Before I go much further with this, I want to show you why this is true. So this is a proof. And this document that I've got up may not be in your workbook, but it's not too long for you to kind of pause and copy this. It says that the logarithm of the product of two numbers, like x times y, the logarithm of the product of two numbers, is equal to the sum of the logarithms of the numbers, the sum of the log of x and the log of y. And so let's talk about y now. Let's let you see why. In mathematics, the only way to prove things is with letters. You cannot do it with numbers. So what mathematicians did here is they let the log of x, where the base is b, be represented by a single letter. We're going to use the letter u. In mathematics, often the letter u and the letter v are used, probably because they're not used a lot in algebra, although v for velocity in physics. So the log of y, where the base is b, is going to be represented by the lowercase letter v. And what they said in order to prove this is they thought, what if I take these two statements and put them in exponential form? Remember, this is an exponent. A logarithm is an exponent. That's my base. So this could also be written as b to the u power is equal to x. And this could also be written as b to the v power is equal to y. Those mathematicians pulled their heads together and they said, I wonder what happens if I multiply these together. So what if I took b to the u times b to the v? Well, b to the u is x, so that would also mean x times y, because b to the v is y. And then they said, well, look, these bases are alike. I should add those exponents because I'm allowed to do that in exponential statements here. If the bases are alike, I'm allowed to add those exponents. And then they said, let's get back to logarithmic form. And remember, a logarithm is an exponent. So this exponent right here is going to be written all by itself. And then I'm going to put the word log over here, and I got to put the little b here because this was the base of b raised to that power. And then this x times y has got to go over here. And so finally, I'm almost done with my proof. Way in the beginning, the letter u represented the log of x, where the base is b. So see right here? I'm going to replace the letter u with the log of x, where the base is b. And see this letter v right here? That's the log of y, where the base is b. So I'm going to replace that with the log of y, where the base is b. And I'll finish the right side of the equation, and it says if I want to take the logarithm of the product of two items, I could also write it as the log of each item in the sum of those two. So let's go back to this worksheet. And so what we're asking you to do is to be versatile with this theorem, the product theorem. So if you have two logs where you have a plus sign in between, you could condense that down into a single logarithm and write that as the product of the log of h times m, where the base is t. So you could simplify this one. So sometimes I want to go from more complicated to more simplified, and sometimes I want to go from simple to more complicated. Could we go back to this one for just, no, let's not do that quite yet. Let's go here. So if I wanted to take this and write it as a single logarithm, because it's the log of 5 plus the log of x, I could write that as a log of 5x. I don't have to write a base. When the base is not written, it's understood to be a base of 10. But I do not have to write it. It's just understood in our world. So anyway, a little bit more complicated to a little bit more simplified. And here, if I want to break that back out, because it says use the theorem logarithm of products to write the following problems either expanded or written back out in simplified form. So I would write this one like this. I want to go back to this one just for a minute with you. Can you tell me what power you would raise 5 to in order to get 25? What power would you raise 5 to? Oh, you'd raise it to the second power. What power would you raise 5 to here to get 125? Oh, you'd raise that to the third power. 5 to the third power is 125. The answer to that problem is also 5. This value right here. So you could take your calculator and find out what 25 times 125 is. Matter of fact, I guess I'm going to go ahead and do it. So 25 times 125 is 3,125. So this problem is also the log of 3,125, where the base is 5. And remember, this could be typed on your calculator by typing the log of 3,125. The older calculators have to have parentheses. Divided by the log of 5. Really, all calculators have to have parentheses, but some of them open it for you. I will tell you that this right here on the newer TI-84s can be gotten at, and I just offhand cannot remember what key you hit to get here, and I don't have a TI-84 in my hand, so that's my dilemma. It's much easier than typing the change of base theorem, because you can actually type it like this, and it allows you to type the base. We'll discuss it in class. We'll figure it out. Before we pause from this particular segment, let's go ahead and look at the quotient rule. So I just want to go back here to the theorem of quotients, and I want to say to you quite quickly, actually, that if this is the letter U and this is the letter V, so I'd have, I guess I'm going to go ahead and actually write U is the log of x, where the base is b, and V is the log of y, where the base is b. If I put these into exponential form, and then if I choose to write them as a quotient, because that's what I'm trying to study about division, so b to the u divided by b to the v would be x divided by y. But right here, because those bases are alike, I could take u minus v. So I'm going to take that over here and write that as b to the u minus v power equals x over y. And now I'm going to put this all back into logarithmic form, so the exponent is all by itself. The base is b of x divided by y, and this now says that the log of x divided by y, where the base is b, could be written instead as the log of x, where the base is b, minus a subtraction problem, the log of y, where the base is b, because that's what v is. And the reason for that is because if you had x to the fifth over x to the second, you would subtract their exponents, and logarithms behave like exponents go. So if you want to divide, you can subtract. So finally, let's go back to this worksheet. And this says, use the logarithm of quotients to write this. So yeah, you know, the log of 27 divided by 9, I want you to know 27 divided by 9 is 3. And the log of 3, where the base is 3, is equal to 1. But what we're trying to get you to write here is we're trying to get you to write the log of 27 minus the log of 9, where the base is 3. The log of 27 minus the log of 9. We're just trying to get you to use the theorem of quotients. Let's go here. So here I want you to put these as one logarithm. So since it's a subtraction problem, you can write it as a division problem. And so also, if it's two numbers and you really can divide them, just go ahead and do it. So 42 divided by 7 is 6. That's how you'll see your answer. Let's go to this one. So this one would be written as the log of a single logarithm, you guys. You've got the difference of two logarithms. It's written as not two word logs, just one word. 81 over 9. And 81 divided by 9 is 9. And so this whole statement means the log of 9, but this is the quotient rule. Here, if I wanted to write it as subtraction, I could write it as the log of the cubed root of z minus the log of 8. Again, I don't have to write the bases because there was no base given, meaning it's a base of 10. So I'm just trying to go from a single logarithm and break it up into two parts, or two logarithms, and because of subtraction, recognize it's a division problem.